Swayam Prabha. Digital India. Educated India.
Now, the thing that we shall learn today is about odd and even signals or odd and even functions. Okay. So, a function is called even if x of t is equal to x of minus t. An example of such function, very common function, is cosine t. A cosine function will look like this. This is time versus cosine t, and you see that the value at some time is same as the value at the negative of minus of that time. X of t is same as minus xt for cosine t, because cosine minus t is same as cosine t. So such graphs look symmetric with respect to the vertical axis or t equal to 0 axis. Similarly, a function is called an odd function or an odd signal if x of t is same as minus x of minus t. One popular example is, of course, sine t. And you know that sine of minus t is same as minus sine t, and a sine curve looks like this. And here you see that this function is symmetric but in a peculiar way. You can call it anti-symmetric with respect to the time equal to 0 axis or the vertical axis. Okay. Now you can have signals which are neither even nor odd. So we may have signals which are neither even or nor odd. For example, consider xt equal to e to the power t. So if we plot this graph, at t equal to 0, xt will be 1, and then it will increase exponentially. On the other hand, it will decrease and asymptotically go towards the 0. So that's how the graph of e to the power t looks like. And you see, it is neither even nor odd. If you flip this signal around the vertical axis, it will not remain symmetric or neither antisymmetric. But the very important thing that we will learn is this fact, that any signal can be broken into a even and a odd signal. So we may have signals which are neither even or nor odd. For example, consider xt equal to e to the power t. So if we plot this graph, at t equal to 0, xt will be 1, and then it will increase exponentially. On the other hand, it will decrease and asymptotically go towards the 0. So that's how the graph of e to the power t looks like. And you see, it is neither even nor odd. If you flip this signal around the vertical axis, it will not remain symmetric or neither antisymmetric. But the very important thing that we will learn is this fact, that any signal can be broken into a even and a odd signal. Any signal can be written as the sum of an even and an odd signal. So this is the statement, very important statement, that any arbitrary signal can be written or expressed as the sum of an even signal and an odd signal. It's a very useful theorem, you may call. Suppose some signal xt is given, which is neither odd nor even. We can always write this xt as xt plus x minus t plus xt minus x minus t, so that this this extra term cancels, but now I have xt twice, so let me divide everything by a factor of 2 and a factor of 2. Okay, you verify that the right hand side is same as the left hand side, xt. Now let me call this part as x even t. This is a function of time, and I am giving this function the name x even. Similarly, I am giving this function a name x of odd t. Okay. Now you can verify that this function x even is a even function. Okay, let's verify. So I'm claiming that this is an even function or even signal, and this is an odd signal. Let us verify. So to verify, what we will do, we will find the value of x even at minus t. Okay, what is this? Let me first write that x even t is same as xt plus x minus t whole divided by 2. This is as per the definition, as I have defined, as I have named it. Okay, so therefore x even minus t will be equal to, in this expression now I have to replace all this t by minus t. So this t will become minus t, and plus this minus t will become plus t whole divided by 2. And you see that this is same as this. This is same as x even t. Therefore, x even minus t is same as x even plus t, and thereby this function is a even function. Okay. Similarly, on this side, let me start with the definition of x odd t, which is this: xt minus x minus t whole divided by 2. And now I will put x odd minus t. Okay, let me put the t here. This was x odd t. Now I am putting minus t in place of t. So replace all t by minus t everywhere. So this becomes x minus t minus x plus t whole divided by 2. Now you compare this expression with this expression, and you will see that this is same as minus x odd t. Okay, therefore x odd t is same as x odd minus t, and that proves that this part is an odd signal, odd function. Okay, therefore any signal, given any signal, odd or even or anything, can always be broken into odd and even as a sum of an even part, even component and odd component. This is a very useful trick, useful theorem, useful result that you must remember. Okay, let us take an example. Suppose xt is given as e to the power jt, where j is the imaginary number root over minus 1, complex number. Okay, then I want to break it into as a sum of an even part and an odd part. So the even part will be x even will be xt plus x minus t whole divided by 2. Now if I put the values, this is same as e to the power jt plus e to the power minus jt whole divided by 2, and this is by definition, this is not called, this is by the definition or by Taylor series expansion. You can prove that this is same as cosine t. Okay. Similarly, you can calculate x odd t, that will be xt minus x minus t whole divided by 2. Now if I put the values, e to the power jt plus e to the power minus jt whole divided by 2, I can multiply this with j and divide by the same term j. Then this part you should recognize is as sine of t multiplied by this factor j. Okay, therefore e to the power jt you should be aware of, this is equal to cosine t plus j into sine t. That's what we see here. Xt is sum of x even, which is cosine t. Cosine function is even function, and the odd part is the sine t. Sine is the odd function. Finally, today we shall talk about or define energy and power of a signal. So for that, you imagine that we have a piece of resistance with value equal to 1, and the current flowing through this resistance is it, a function of time or a signal. Now for this situation, instantaneous power at any moment is given by the Joule's law, I t square r, and r is equal to 1, so multiplied by 1. Now therefore the total energy dissipated or associated with this signal it can be written as integration of I square t, which is this, multiplied by dt from the maybe from minus infinity to plus infinity. That is throughout the time span we can imagine. Now this is the total energy, and therefore we can calculate average power which will be the total energy divided by the total time. Now in this case total time is infinite, so let me write it this way. Say starting from time minus t to time plus t, and then divide it with total time span 2t, and let this t tend to infinity in limit. So limit t tending to infinity 1 over 2t integration minus t to plus t I square dt is the average power consumed. Now keeping this in mind, we define the energy of a general signal general function of time xt as integration of x square t dt from minus infinity to plus infinity, and you may also write it this way, minus t2 plus t with limit t tending to infinity. This is the total energy. Now this x may be current or maybe some other physical quantity, and therefore this energy might not be the energy that we study in physics. This may not be heat energy or any similar energy, but this is the definition of energy of any signal. It may be physically same as physical energy or may not be, doesn't matter. And similarly, the average power of a signal is defined as the total energy divided by total time. Okay, again this physically need not represent power in watt. Okay, but this is the mathematical definition of power of any signal or any function. Now consider a signal which spans for a short duration, maybe like this. After this point the signal is 0, before this point the signal is 0. Call it xt. Now if you calculate the energy that is integration of x square t dt from minus t to plus t with limit t tending to infinity, you will get some finite number. Essentially, you have to carry out this integration from this point to this point. After that or before that, the integration will result in 0. But if you calculate power of this signal, so you have to divide the energy by 2t, then you shall get 0. As you take larger and larger value of time, the total energy is going to remain same, but you are dividing with larger and larger value of time, so you will get smaller and smaller value of power. In the limit, it will give you 0. So we define energy signal as the signals for which energy is finite but power is 0. Such signals are called energy signals. Now on the other hand, consider a signal, say, which is, for example, periodic, and say that is sine omega t. So it continues on both the sides of, I mean, starting from minus infinity to plus infinity. Suppose this is sine omega t. Then if you calculate energy, that means you have to do the integration from minus infinity to plus infinity, x square t, that is sine square t dt, you will get infinite. As you take larger and larger value of time, your result of integration will be larger and larger. But if you calculate power, that is, let me write again, that is going to give you a finite number. Because as the range of time increases, the total energy increases, and proportionally the time also increases. So when you divide the total energy by time, you get a finite number. And you know that if it is sine omega t, in that case the result will come out to be 1 over 2. So in power signals, to be signals for which energy is infinite but power is finite. Let me first draw a signal whose value is equal to half within the region that time is greater than -1 and less than +1. After this time, the signal goes down to 0 and remains 0 forever after. Before time equal to -1, the signal was also 0. Now let me calculate the area under this curve or signal, and the area is given by the width of this curve, which is 2 unit, multiplied by the height of this curve, which is half unit, so the area is 1 unit. Let me now draw another curve which is taller than this yellow curve, whose value is equal to 1, but this curve is also narrower than the yellow curve. So it goes down to 0 at time equal to half, and before time equal to minus half it was also 0, and after this point this is again 0. Now the area under this green curve is given by the width of this curve, which is 1, multiplied by the height, which is also 1, so the area is 1. Next, I shall draw another curve which is even taller, whose value is equal to 2, but this is narrower than the previous two curves, which goes down to 0 at t equal to 1/4 and remains at 0 ever after, which is also 0 before the time t equal to minus 1/4, and only within this narrow region its height is 2. Now the area under this blue curve is equal to the width, which is half unit, multiplied by the height, which is 2 units, so the area is again 1. This way I can continue to draw signals which are taller and taller and taller than the previous signals, but at the same time they will be narrower or thinner than the previous signals. For example, I can define a signal, call it xt, which is 0 outside the region, say t equals plus epsilon and t equals minus epsilon. So between these two times, t equals plus epsilon and minus epsilon, the signal is non-zero, and outside the signal will be 0. Let me write it this way, that xt is equal to 1 over 2 epsilon if time is less than epsilon and is greater than minus epsilon. Within this region, the height of the signal is 1 over 2 epsilon, but outside this region, the height of the signal is 0. Now let the width of xt, which is same as 2 epsilon, be very small, or let it go close to 10 to 0. Under that situation, you can imagine a signal which is extremely narrow, but its height will also tend to infinity. So under that situation, the height which is 1 over 2 epsilon, that tends to infinity. But no matter whatever value I choose for epsilon, the area under the curve xt will be equal to 2 epsilon multiplied by 1 by 2 epsilon, which is same as 1. So area is constant. However, as I change epsilon, the signal becomes narrower and narrower and narrower and taller and taller and taller. Now the extreme situation when epsilon tends to 0, that extreme signal that you can imagine is called an impulse signal or an unit impulse signal. Okay, now that we shall draw in this way. Let this be the time axis, and now that extreme signal is so small, so narrow, that its value is 0 soon after time t equal to 0, and soon before time t equal to 0, the signal is again 0. Now within this very narrow region, its height will be very large, and so we shall draw it with a single line because it is very narrow. So we will use a single line, but we cannot draw an infinitely long line, so we shall put an arrow to denote that this signal goes or tends towards infinity. This is the symbol of an impulse function. This is time equal to 0. So this is the symbol of an impulse function, which is also called a delta function or delta signal, and is normally denoted with the Greek alphabet delta of time t. Mathematically, we shall define this function in this way. Delta t will have a value of 0 if time is greater than 0 plus. If time is slightly greater than 0, then the delta t will become 0. Its value will also be 0 if time is slightly less than the 0 or 0 minus. The value of the signal will be very high between this region 0 minus and 0 plus. However, the area under the curve, which is same as the integration of the signal delta t multiplied by dt from time equal to minus infinity to plus infinity. This integral gives the area under a curve. This is equal to 1. The signal is very narrow but very tall, so the area is neither 0 neither very large, but it's a finite number. And this is the mathematical definition of an impulse function or an unit impulse function. So this is called an unit impulse signal. Unit because the area under the signal is 1. An impulse function is slightly difficult to visualize or imagine But now we shall look at some simpler functions. Unit step function or step signal. This is defined as follows. It is normally denoted with the letter U and its value is equal to 0 if time is less than 0 and its value is equal to 1 if time is greater than 0. That is the definition. Now let me draw this signal. If this is time axis, this is t equal to 0. If this point has a height of 1, then the value of ut is equal to 1 after time 0 and its value is equal to 0 before time 0. This is u of t. Let me define another simple signal which we call an unit ramp signal, which is defined in this way. R of t, R for ramp, is equal to 0 if time is less than 0 or less than equal to 0 and its value is same as t if time is greater than or equal to 0. Let me draw this ramp signal. So before time t equal to 0, the value of this signal is going to be 0 and after this point it will increase with a slope of 45 degree. So this signal is called R of t, ramp signal or unit ramp signal. Now let me ask, how will the signal ddt, that is the time derivative of rt, will look like? So this is rt and we want to find how the derivative, time derivative of rt will look like. Let me draw. Observe that before t equals 0, rt is constant and therefore its derivative will also be 0. So before time equals 0, the derivative of ramp signal is 0. After time t equal to 0, rt increases with a constant slope. That slope is 1. So the derivative after t equal to 0 will be a constant equal to 1. So this is time versus ddt of rt. So you observe that this signal is same as the unit impulse signal. So this is a very useful result, that the derivative, time derivative of an unit ramp signal is same as the unit impulse signal will remain. So this is also a very useful result, that the integration integration of unit step function is same as the ramp function, and the opposite is also true. The derivative of ramp function is same as the unit step function. Now I shall ask the question that if I differentiate ddt an unit step function, what shall I get? Let me draw the step function. I shall draw an approximate ut, which is not ut, some approximate ut, and which looks like this. It is 0 before t equal to -1, and then it goes up slowly, gradually, linearly, and it becomes 1 at t equal to 1, and then it remains at that value. Now I can differentiate this approximate curve, and if I do that, ddt of approximate ut, that will have a value of 0 before this point because the function is constant. After t equal to 1, again the function is constant, so the derivative will be 0. And within this region, it increases linearly. So the derivative will be the slope, and the slope is half. So its value will be like this. So this is the derivative of approximate ut. Now, in the next step, I shall do a better approximation of ut, which looks like this. It is 0 from -infinity up to this point t equal to -half. Then it will go up gradually, and after t equal to half, it will become 1. So this is t equal to half. And the derivative of this approximation will be as follows. It will be 0 from -infinity to -half. After +half, it will be again 0. But within this region, -half to +half, it increases linearly, and the slope is 1 unit. So that will look like this. This is 1 unit. This way I can keep drawing better and better approximation of ut, which goes up faster like this. And therefore the derivative will also look like constant before some point t equal to minus something, and after some point it will again be 0, but within that narrow region it will have a high value. Now I leave it to you to verify that the area under any of these curves, is equal to 1. This red curve or this green curve or the white curve, which are approximations of this derivative, all have constant area under them. And if I keep doing better and better approximation, you shall realize that the result is going to be narrower and narrower, taller and taller, However, the area shall remain constant equal to 1, and this is nothing but our unit impulse function. When you take the extreme limit, when you imagine the extreme limit, this is going to be our unit impulse function. So the result is that ddt of, let me write here, ddt of ut is equal to delta t. I can also ask the opposite question, that what is the value of this integration of delta t from time t equal to minus infinity to t equal to some constant capital T. How much is this? Let me draw the delta function. Time, this is t equals 0, and the delta function is denoted with an arrow. This is unit delta function, delta t. And if I integrate the area under this curve, then the result will be as follows. The result will be 0 if capital T is less than 0, because here delta T is constantly 0. However, if this time T is somewhere on the right side, then the area under the curve will be the area under this delta function, which is same as 1. That is by definition. So if t is greater than 0, then this integration result in 1, and if t, capital T is somewhere on this side, then the result will be 0. And you should now recognize that this is the definition of our ut. So this is again another important result. The derivative of ut is delta t, and the integration of delta t is ut. This should be capital T, okay? Because this is a function of capital T and not of small t. Yeah, okay. At this point, I will just tell you a fact that previously I told integration of delta T from minus infinity to plus infinity, that is the total area under the curve, is equal to 1, but I can also write that the integration of delta t from t equals 0 minus to t equals 0 plus, any number slightly greater than 0 and any number any number slightly less than 0 and any number slightly greater than 0. Between this region, if you do the integration, that will also be equal to 1. Okay, because the entire area is squeezed within this narrow region. Outside this, the area is anyway 0. This side area is again 0. So within this narrow region, the area is 1, and therefore the total area, which is this integration, that is also 1. Okay, let us now recall the definition of delta t, that delta t is equal to 0 if time is slightly greater or slightly less than 0, equivalently if time is not equal to 0. However, the area, which is the integration of minus infinity to plus infinity delta t dt is equal to 1. This is the definition of delta t. Now, imagine another function yt, which is k times delta t. So this is amplitude scaling of delta t. What can we say about yt? We can say that yt is equal to 0 unless time is 0, because if t is not equal to 0, then delta t is 0. 0 multiplied by k is 0. However, the area under this curve yt dt from minus infinity to infinity, that is same as the area under k delta t dt, and since k is a constant, I can take k outside, and this integration is 1, therefore this is equal to k. To visualize this, you imagine that I plot time versus delta t, and delta t is a very narrow signal and very tall, and the area within this curve is 1 unit. This is delta t, whose area is 1. Now if I plot time versus k times delta t, then that will be k times taller than delta t. So it is more tall, and the height is increased by a factor of k. This is k delta t, and the area will be k times 1. Okay. Now let me ask a very important question. Suppose I define yt, a function which is xt, some other arbitrary function, multiplied by delta t. Then this is equal to what? Let me draw first some arbitrary signal, time versus some arbitrary signal which is like this. This is x of t, and let me also draw delta t on the same picture. So delta t is 0, and here delta t picks up. We denote that with an arrow, and then it comes down and becomes 0 again. This is delta t. Now if we take the product of these two signals, then the result will be, of course, 0 in this region, because delta t is 0. In this region again the product will be 0, but at time t equal to 0 it is not 0. Let me zoom into this part. So if I zoom in, then I shall see a very tall signal delta t, very narrow. So this is delta t, and let me also draw xt. Xt in this part within this small narrow region is fairly constant. This is xt zoomed in, and the height of xt at this point is same as x of 0. Now if you multiply these two signals, the product will look like delta t being multiplied by the constant x0. So the product will be taller than delta t, and therefore the area under this curve, which is delta t multiplied by x0, the area will be x0. So what we can say is that yt is a curve such that this is equal to 0 if t greater than 0 or if t less than 0, and the integration of yt or the area under this curve is equal to x0. This is a constant number, and therefore yt is very similar to delta t, but it is larger than delta t. So we can say that yt is x0 times larger than delta t. This is a very important result. Okay, I should rather write it here. This is same as x0 times delta t, and therefore as I said, xt delta t is same as x0, a constant number, multiplied by delta t. So it implies that the integration of xt multiplied by delta t from time t equals minus infinity to plus infinity dt will be same as x0 delta t integrated minus infinity to plus infinity dt, and this is same as x0 integration of delta t dt. Since x0 is a constant, I can take it outside the integration, and the result is x0. So I can in fact also say that xt delta t, this integration, instead of taking it from minus infinity to infinity, I can also just integrate around the origin 0 minus to 0 plus, because that is where this signal is non-zero. So therefore the integration from 0 minus to 0 plus is same as the complete integration, and the result is equal to x of 0. So this result you must remember throughout your life or throughout the course. Now let me ask another question. If I define a signal yt, which is some arbitrary signal xt multiplied by delta t minus t, and this capital T is a constant number given. Okay, for example, let me take this to be equal to, say, minus 5. How will this signal look like, or what will be the result? Let me first draw some arbitrary signal. Let this be an arbitrary signal x of t, and delta t minus 5 will be here 1, 2, 3, 4, 5. At this point, this is delta t minus 5. The height of xt at this point can be written as x of 5. Now if you multiply xt and delta t minus 5, then the result will be, of course, 0 in this part, will also be 0 in this part, but will not be 0 at t equal to 5. And at t equal to 5, the product or yt will have some area under it, and the area under yt, at or near t equals 5 will be delta of 2t. K is some constant, let that be 2. How will that signal look like? Let me draw that in this way. Delta t is a very narrow spike near the origin, near time t equal to 0. So let this point, although I am drawing it quite large, let this be 0 minus and let this be 0 plus. So I am zooming in near the time t equal to 0. This is delta t, and now if I draw delta kt, this is time scaling of delta t. For example, if k is equal to 2, then this signal will be compressed or squeezed along the time axis by a factor of half. So this will become like this, more narrow, but the height will remain same. This signal is delta 2t, and the area under this curve is, of course, half of the area of delta t. So the area under delta 2t is equal to half. In general, the area under delta kt will be 1 over k. So this signal is therefore again an impulse signal which is non-zero only near the origin and 0 everywhere else. But the area under this curve is finite. It is not equal to 1, but it is equal to 2, or it is equal to half, or 1 over k. Therefore, I can write this is equal to half of delta t. Similarly, delta of kt is equal to 1 over k delta t, and this is again a very useful result that you should remember. I think today we have enough mathematics, enough new and puzzling stuff. So in the rest of the class, we shall take up some lighter topic and we shall discuss about systems. My train is very simple. It has only one control, which is this lever. If I push this lever up, then the train gains speed, and if I pull it down, then the train slows down and eventually stops. So this is the input to my train, and the output from my train is the speed. In other words, the change of position of this lever is the cause of speed change, and change of speed is the effect of varying the position of this lever. Now, my goal in this game is to reach my destination station as quickly as possible. Therefore, I shall push this lever up to the extreme highest position so that my train gets its maximum speed and I shall reach my station as quickly as possible. But soon after, when I see the station is approaching me, then I have to pull this lever down so that the train stops at the platform. However, the train doesn't stop. It continues to run due to inertia, and I encounter an accident. Now I can retry this game, and this time I will keep the speed very low so that I can stop the train whenever I want very quickly. But if I keep the speed of the train very slow, then I shall reach my destination station very late. Now this problem arises because I do not know exactly how much to increase the speed and exactly when to decrease it. The relation between this input and the output, which is the speed, is not very well known to me. I do not know very well the relation between the input and the output or the speed, and that's why I do not know how to manage this situation. Now, the input or the position of the lever can be changed with time. As time changes, I can also change the position of this lever or the input up or down. Let me draw a curve where the x-axis denotes time and the y-axis denotes the input to the train as a function of time. Now I can raise this position high at the beginning and then after a while I can bring it down. As a result, the speed of the train also changes as a function of time. Let me plot another curve where the x-axis is time and y-axis is the speed of the train as a function of time. When I increase the input, the speed also increases, but slowly. It keeps increasing up to this point. When I decrease this lever position, but then the speed does not become zero instantaneously, but it goes down to zero slowly. This is how the input as a function of time and output as a function of time looks like. Now, if I were an experienced driver, if I knew the relation between this input and this output pattern, then I could reach my destination very quickly in the smallest possible time, in the shortest possible time without making an accident. But since I am not that experienced, I cannot do that. But not only an experienced driver can drive this train well, also machines or computers can drive trains very precisely. Platforms in many advanced countries are secured with screened doors like this. And the train is often driven automatically without any human driver. Such trains which are driven automatically can stop very precisely at the correct position so that the doors of the train and the doors of the platform are perfectly aligned. This is possible even when the train is driven by a computer without any manual intervention. Now think of an aircraft in place of a train. An aircraft is much more complex compared to a train. It has many inputs. You can control the pitch angle, the roll, the yaw with the joystick. You can control the thrust to the engine. You can control the flap position. You can control the rudder position. So it has many inputs. And what is the output? Output is the 3D position of this aircraft in the air. So both the number of input is more than one and the number of output is also more than one. And the relation between the input and output is more complex than a train. However, you must be aware of that often an aircraft can be driven completely with autopilot without any human intervention. That is possible because the autopilot or the computer knows the relationship between various inputs to this aircraft and its output very well. Let us now ask, what is a system? Any object, any machine which has one or more inputs and one or more outputs, that can be considered as a system. We call that a system. A train can be a system, an aircraft can be a system, a car can be a system, where the inputs are the position of the steering, the position of brake, accelerator pedal, etc. And the output of the car is its speed or position or acceleration, etc. A simple motor can be a system. The voltage that you apply to the motor, that is the input, and the speed of the motor could be the output. A generator can be a system. So the speed at which the generator is driven, that could be the input, and the voltage generated, that could be the output. A turbine can be a system. The amount of steam that you feed, that is the input, and the power or speed of the turbine, that is the output. So any machine, any object which has input, output, and some relation between its inputs and outputs, that can be considered as a system. So that is what I said. Any machine is a system. Now, the inputs and the outputs of a machine or a system, they can vary with time. So input and outputs are functions of time, therefore they are signals, and that's why we are studying about signals. Now, to be able to control a machine properly, we need to understand the relation between its inputs and outputs very well. We can often ask questions of the form that given a system, for example our train, and some known input pattern, that is, say, how I am varying the position of the lever with respect to time. So given the input, how will the output vary? That means how will the train move? So we can ask, if I know the input, how will the output change? Input is also known by the term excitation, and output is also known by the term response. Now I can ask the opposite question, like, say, given a system like our train, and if we have a desired output, that means if we want the train to move in a particular way, then what kind of input or excitation is required? So given I know how the train should move, how should I control the position of the lever? This is the opposite question. One can also ask questions of the form that, can I make a system whose input-output relationship is as I desire? For example, we saw in case of our train, the output or the speed doesn't change instantaneously when I change the input. There was a delay due to inertia. Now, can I make a train so that there is no delay between the input and output? Then it will be more easy for me to control that train, and it will be less likely to make fault or accident. All these questions are asked and investigated in the subject called system science or system theory, which is what we are studying in this course. Thank you and have a very nice day.